Hello everybody. So I welcome you to my next class. Today we are going to talk about a very important topic in this class of financial engineering, which is essential to what we will do next week. Because next week, I promise you, we go back to finance, in particular the pricing question. But before we can do this today, we will talk about stochastics. So I will give you an introduction into stochastic processes. How are stochastic processes defined? How can we handle a function that is dependent on a stochastic variable? And in particular, when we have a kind of continuous function, the question is, how can we calculate or compute the derivative? Or how can we do integration with a stochastic function or variable? And that's the topic we are going to talk about today. And that is chapter 4, basically in my lecture notes, and chapter 5. Before we start with the mathematical background, I will give you a kind of motivation, a graphical motivation, because you will see it's a lot of new things you will see today and learn probably. And I will show you some stochastic process here at the beginning. And what you can see on the screen so far is a simulation program that is called MATLAB. And we have here a license. By the way, for the first time, we also have student license in the group, in the same computer pool in Building 5, where we have the FactSet toolbox installed. And this simulation program, MATLAB, allows us to do lots of computation, mathematical computation. And here I have a very simple program, which is simulating what we call a Wiener or a Brownian motion, a Wiener process or a Brownian motion. So if I click here on Run, you will see a curve pops up. And here you see a kind of level. Yeah, so it starts here in 0, goes up until 5, around 5, but it can also go down, obviously. And then here you can say this is the time period. Yeah, so there are 1,000 time steps. So this is a curve which, if you look at this curve, you may say, well, that looks like a stock, maybe Microsoft or like the Dow Jones index over some time period. Actually, it is not a time series. It's not based on data, this curve. This curve is just simulated based on my program. And I can run the program once again. So here is the picture. And if I click once again on Run, and now we take a look to the graph, you see now a new curve, this red one. Once again, this is a curve which is not based on data, it's based on simulation. And these two curves, and even more, you can do hundreds of simulations, obviously, of such curves. This is what we call a stochastic process, or a Brownian motion, or a synonym for this is a Wiener process. And today, I will give you some idea what is a stochastic process? First I start with the definition, then I describe the properties of a stochastic process, and then I ask the question, how can we handle a function dependent on such a stochastic process? So regarding how can we do differentiation, integration. And we will see that some of the rules you have learned in high school and here business mathematics regarding integration and differentiation, the rules are here different. So there are new rules in terms of integration and differentiation when we have to handle stochastic processes. Well, you will see there is usually they are split in two parts. One part is, as you already know from high school, and then there's always a new part that pops up due to stochastics. And we will discuss also this, the rules of differentiation and integration of functions dependent on stochastic processes.
So this is just a random simulation?
Right. So behind this is a random process. So a random number generator. So this MATLAB program has a random number generator. So it randomly generates numbers. And then with certain properties, you obtain such curves. Yeah, and the properties is what is in the code, which I have programmed here, which you can see here in this screen. Okay, so now we start with the introduction to stochastics, the topic of today, which is chapter 4 in my lecture notes. So, intro to stochastics. And I will start with a definition. So what is a stochastic process? And you will see how all the topics we have talked about already come together today in a way. Because last week, if you remember, we talked about random variables. Yeah, and I said, well, we label random variables always with capital letters like X or Y. And you know, a random variable was an event. Well, for instance, if we roll a dice, and at some time you will see the 1, at sometimes the 4, and if you roll it again, maybe once again the 4. So the event is random. We don't know what pops up at the end, and that is what we labeled a random variable. And a stochastic process is very close to this idea. In the end, it's a sequence of random variables. A stochastic process is defined as a sequence of random variables. So if we have random events over time, that is what we label or call a stochastic process. So definition, stochastic process, and I will call it also X, but now it's a set dependent on T. Yeah, it's a sequence of random variables over time. And let's say T starts at 0 and then continues. So a stochastic process, X of T of this set, stochastic process is a sequence of random variables. So this is the easiest way to get some idea about when I say stochastic process, what is behind this. It's a sequence, the stochastic process, xt for t greater than 0, is a sequence of random variables.
Could you give a short definition for t?
Well, t is time, so you can say t runs, t is element if we define the beginning 0, yeah? And it runs in extreme until infinity. But we can stop, you know, when we talk about our option, we can say we start at some year, and the end is not infinity, it's our capital T, the expiration day, for instance. Yeah? So T is time. And the small t, as I already mentioned in one of my first classes, is always the time today somehow, yeah? And capital T would be the time at the end. If I distinguish, I will always say this, but that's a kind of convention you can always use here in this class. Okay, so a stochastic process xt is a sequence of random variables. And what we have to do now in this session, in this class today is, well, we have to define a little bit what are the properties of this sequence of random variables, yeah? And we will see there are certain properties. And if I give you, before I will do these definitions, what are the properties of a stochastic process, I will give you a second motivation, apart from the graphs I showed you in the beginning, that moves us a little bit back to a topic you learned in my macroeconomics class. So, can I say motivation? So, probably all of you remember that in macroeconomics, at some point we talked about a dynamic model. It was the Solow growth theory. And the key feature of the Solow model, in comparison to other models you learned in microeconomics and also in macroeconomics, it was dynamic. So the variables were all dependent on time. And probably some of you remember that the key modeling of a dynamic model, or a dynamic variable, is via differential equations. And if you remember, well, there were a couple of equations, but at some point we assumed that the population growth rate, and we labeled this with a small n, we said this is a change of the labor variable over time divided by the labor variable dependent on time t. So a growth rate was always the change of the variable over time, LT dot. This is the first derivative of this function in respect of time, LT dot, divided by this function LT equals n, the population growth rate. And we assume that the population growth rate in the Solow model, now that is an assumption we used in the Solow model in macroeconomics in the third semester. We assume that this growth rate is constant. And, well, if I rearrange this equation a little bit, we can write it down and say, well, this is first derivative in respect of time, so LT dot is equal to n times, and if I just move the LT on the other side, then we have this. And I told you in the third semester, whenever we have an equation where we have the function and the derivative of the function, then we call this a differential equation. And due to the fact that we have a first derivative, one dot in respect of time, it's a first order differential equation. If we have a second derivative, we would call it a second order differential equation. So this is a first order, what we call ordinary differential equation, simple differential equation. And this is modeling, you can say, the population growth rate or the behavior of our labor force over time. Now, why I'm telling you this? Well, because we will see that whenever we have to deal with dynamic processes over time, the only way to handle these or to model this mathematically requires differential equations. So when we talk about a stochastic process is a sequence of a variable over time, a random variable over time, definitely what will pop up later on many times are certain differential equations. And due to the fact that we have a stochastic variable, we will see that are not ordinary differential equations, that are so-called stochastic differential equations. So let me give the idea here. So in this case, as I already mentioned, we assume that n, the population growth rate, is constant. But actually, this is a strong assumption, right? If you look to the fertility rates in Germany, obviously they were far higher in the 50s and the 60s than they are today, though they are changing over time. So it's far more realistic. So if we intend to model this in a more realistic real-world way, well, we have to say, well, this population growth rate n is also a variable that changes over time. And, well, let's say there are two factors we have to consider. One is, I call this here R of t. And the R is, let's say there's a trend in fertility, right? Due to the fact that people are higher educated now, fertility is going down. And that is a kind of common trend you can observe in all societies. The more educated the people, the lower are the fertility rates. So this is an easy trend you can basically predict in a deterministic way. There's no stochastics about this. It's like a deterministic trend, so the first component. But then, let me add to this change of fertility over time a second component. And this component, well, I write here sigma of t, which is a kind of volatility, some fluctuations, times what I label for a second SP, which is a stochastic process. So SP is a short for a stochastic process. So what does this second term is telling us? Well, fertility is dependent on a trend, first term, plus some fluctuations which are stochastic around this trend. So in another words, we can say, if we look over time to my fertility rate, maybe we will see some, we will see some curves. And you can say here we have a kind of upward trend, then maybe here we have a kind of sideways trend, and here we have a downward trend, an upward trend. So this component is modeling these trend lines, and the second component is modeling these fluctuations around this trend, sometimes up, sometimes below. That is mathematically captured by this second component. And once again, we have to study today a little bit more what is really this stochastic process. So how can we model these ups and downs around these trend curves, which are sometimes up and sometimes down?
Just a question. So n is also dependent upon time, but is there a necessity for us to give that already? Because we already have n is defined by L derivative divided by LT. Both are dependent on time already, so why are we giving the time as a factor of the fluctuation again?
Okay. Here in the solo model, you can say this is a kind of growth rate, what is here on the left-hand side. And we say the growth rate is equal to a fixed number n. Maybe population growth rate is always 3%. Then n is 0.033%. Yeah, because I say here n is not changing. It's always 3% forever. From 2,000 years ago until today. That's not realistic, right? Population growth has changed over time. So if we set up a more realistic model, we have to assume, well, n is also a process. The growth rate of labor is also changing over time as the society changes over time. And that is captured by this, let's say, equation. And we will see this is later on close to a stochastic differential equation, but wait a second. That is what we will see during the class today. So if we assume now that this n is dependent on time, so what I do now, obviously, I substitute this n back into this equation. Why not? It's just a more realistic model then. So then we have LT dot dependent on t is this equation. By the way, maybe I make an intermediate step. How can I write down LT dot? Well, this is the derivative of L in respect of time, right? This is the LT dot, as I mentioned, is just the first derivative of my function in respect of time. So then I say, well, n, and for n I write down this new term, which is R plus sigma times my stochastic process times L. So now we have this line. And now in the next step, I just rearrange this. So what do I rearrange? Well, if I take a look to this, I just bring the dt, which is here in the denominator on the other side. And then I multiply, then the LT is times dt pops up here. I multiply these components into the bracket. So on the left-hand side, we have then d of LT, and then the first component is my trend times LT times dt, right? Because the dt is now here, plus sigma, and then we have this LT, we have this stochastic process, and we have a dt as well. So now we have just slightly rearranged to the dt on this side and then multiplied into the brackets. Already in macroeconomics, we solved this simple equation. And if some of you remember, the solution of a differential equation yeah, this is an ODE, an ordinary differential equation, is always a function. In the end, we are looking for a function that satisfies this equation. And obviously, in this case, it was a simple exponential function, n times t in the exponent, the population growth rate times time. That was the function that is satisfying this differential equation. And the same question is now here. Now we have a differential equation, and we are interested in what is the L that is satisfying such a differential equation, or in this case, this. So how can I find the L? So I'm interested in the other words, I want to have down here the function LT that is telling me how the population evolves over time. So to do this, well, I integrate this function over time from 0 to t, all the terms, here and here. So we have to do the integration. And now you see immediately, well, here we have the integral, here we have the derivative. They are canceling out each other, so what remains is the L at the limit of t. And that is already here. You can say that is LT. And then usually when we do integration, we have a kind of constant, our starting point, which I define as L0, so the population at a starting point. And then we have these two integrals on the right-hand side. So we have to do integration from 0 to t, RT times LT over dt, plus the integration 0t sigma t LT stochastic process dt. Well, the question that now pops up, what is really this SP, this stochastic process, right? So far I have not really defined, that is what we will do in a minute. I have not defined what is a stochastic process. But I will already give you some idea what we are doing in a minute. Well, we define a stochastic process and we label it usually with either a B or a W. The B stands for a Brownian motion. And it's a process, it's a random variable, you can say, over time. It's like my xt, I said, it's a stochastic process. Here I say it's B over time. And therefore, obviously, if this is the case, well, you can say the change of this variable over time, right, is the first derivative. Or in other words, this is dB over dt, right? Well, the change of a variable over time is bt dot, which is dB over dt. And that brings me back to here. So if we look to this term, you can say this is actually the change of my random variable over time. It's bt dot times dt. Can you see that if I bring the dt on the other side, that we have bt dot times dt is the same as d of bt, right? That follows from here. So in other words, here the left-hand side is the same as this term. So in other words, I can rewrite this blue term and write down this. So what we have here in the end is dBt. And that means we have to integrate over this stochastic process. So what we obtain here in this integral, this, is a stochastic integral. So here we have to integrate not about x, a deterministic variable like x or y. We have to integrate over a stochastic process, which I call here B for a Brownian motion. And therefore we call this here, this second integral, a stochastic integral. And we have to study today, first of all, what is a Brownian motion? What are the properties mathematically? And how can we find a stochastic integral? And you see it pops up immediately if we make a more realistic model of the population growth model. This is a simple population growth model we used in macroeconomics. In a more realistic population growth model, when the growth rate is not deterministic and constant, well, immediately we face the problem of handling stochastic variables. What about this first integral? So here we have an integral about our trend variable, our labor force function, over time dt. Well, dt, that's the time you asked. T is a time variable. And time is deterministic, right? Time is running. I can predict after 1 minute, it's 1 minute later. There is no stochastics. Yeah? So time is a deterministic variable. And therefore this integral is what you can do already with high school mathematics or business mathematics you have learned. This is a simple integral that follows the same rules you have already learned. We call this in mathematics a Riemann integral. Yeah? So the Riemann integral is the integral you know. Riemann was a great mathematician, German mathematician, and he defined this type of integral. And by the way, all this integration and differentiation started also by an English and a German guy. One was Newton, and the German guy was Leibniz. They were starting the discussion how to handle functions over time, and then Riemann was the guy who made the rules precise regarding integration, and therefore we call it Riemann integral. This is easy, right? The first integral is boring. What interests us here today is how to do the second integral, the stochastic. Yeah? This is what we call the stochastic integral. Stochastic integral. And actually, there's also a guy involved with this, and we will learn how to do this by Ito. It's the Ito's formula or Ito's lemma. You can say that is the integration of that stochastic integral follows Ito's lemma. And that is what we are learning today. Yeah.
Is there an accent on both?
Yeah, there is a kind of hat, a little hat. Yeah, Ito's lemma. Okay, so let me sum up my motivation. Whenever we have to deal with dynamics, you have to keep in mind, well, immediately what pops up is a differential equation. Dynamics is always linked. A simple growth rate is defined by a differential equation. Dynamics means change over time. A variable is changing over time. That is dynamics. So whenever a professor is teaching you something in dynamics and he's not working with differential equations, then you know immediately he's not talking about dynamics, because the only way to handle dynamics means differential equation. That's the only way to deal with dynamic processes, change over time. Differential equations. And when we set up more realistic models, yeah, this is, you can say, an easy model, which is okay for third semester undergrads in macroeconomics. That's what we did. Now we are advanced undergrads. If we assume more realistic assumption for our fertility rate, for the growth rate, for instance, that it follows a trend in some random process, well, we immediately find kind of stochastic differential equations. That was what we got here. And then we have to solve these stochastic differential equations by integration to find this function, right? To find the population function over time. And that shows you, well, if this is what we want to understand, well, we have to understand obviously what is a stochastic process, B, and how can we do differentiation and integration of these processes or variables. Before I start with a precise mathematical definition of the properties, let me give you a brief history of stochastic calculus or analysis. So brief history, wrong color. So the idea of stochastics started in 1828. And it was by Robert Brown. And by the way, due to that, we call the stochastic processes in books a Brownian motion.
Was he British?
A Scottish botanist. Robert Brown was a Scottish botanist. And what he did, well, he studied pollen grain in water. Yeah, so he looked to the kind of box of water, and there was these pollen, and over time they were flowing around. Yeah, on this two-dimensional surface of water in all directions. Yeah, so there was a kind of box. Yeah, and at the beginning he put some pollen in here, and then he looked how this is flowing around. And well, he realized, well, it's quite hard to predict where it is after some time. Yeah, so it goes sometimes to the left, sometimes to the right, sometimes up, down, and so on in all directions. And well, it turns out that this is kind of a stochastic process. Yeah, the outcome, it's like a random variable over time. We don't know what is the outcome, when, at which position over time this particle is, right? And that was the first time when this idea of a stochastic process popped up in literature. And then the first reference to finance was in 1900 by Bachelier, a French guy. Well, what Bachelier did, well, he looked to financial time series like stocks and other prices and so on. And then he said, well, the prices move up and down like crazy curves, right? We cannot really predict. And he had some knowledge, yeah, from the idea by Brown. And therefore, Bachelier identified and said, well, it turns out that maybe financial time series are similar to stochastic processes we also see in nature. But at that time, keep in mind, there was no way and no understanding how can I model, how can I handle stochastic process mathematically. It was just discovered and looked to this problem. Then in another field, in 1905, there was another great guy, Albert Einstein. Albert Einstein published the famous paper in 1905 about black body radiation. And in this paper he derived a transition density using a Brownian motion, which is a physical phenomena. And by the way, Einstein got the Nobel Prize for this publication, not for the relativity theory. Yeah? So in this publication, already Einstein used the idea of a Brownian motion in physics, but once again, from a mathematical point of view, it was not clear at that time really how to handle, what are the properties, how can we really do integration and differentiation. So he just applied it in a way and used it for a physical problem. The first mathematical definition and approach was in the 20s. So it was 1923-24 by Norbert Wiener, a US-American mathematician. And due to the fact that Wiener was the first guy who really set up the properties we will learn in a second, we sometimes also refer what we call either a Brownian motion or a Wiener process. And that's, you can say, a kind of synonym. They are both stochastic processes. One is referring to Brown, the guy who initially detected or discovered this phenomena, and Wiener was the guy who really set up the rules of a Brownian motion. Well, that was obviously not the end, because the Wiener process is a very special process. There were a generalization of Wiener processes in 1938 and 48 by Levy. He generalized the idea of a Brownian motion, and we call these Levy processes. We will not handle this here, otherwise you will hate me anyway. You know. So this is a generalization, which is just interesting, obviously, from a mathematical point of view, to be more realistic. Yeah, there's some reason, obviously, behind this. At that time, once again, integration, differentiation, no. The first integration and differentiation was set up in 1949 by Ito. Yeah, which is Ito's lemma. That was done in 1949. So that's, you know, if you look into the history of science, quite recent. Yeah? If you think about what you learned in high school, Newton and Leibniz, right? That is hundreds of years ago. What we do now today, integration and differentiation of stochastic function, is just 60 or a little bit more than 60 years ago. And by the way, Ito integration of stochastic function is just one possibility. There are other possibilities, and I will give you at least some idea why today. And that was first developed in 1966, so far later, and that is what we call the Stratonovich integral by Stratonovich. So that was also a mathematician who kind of generalized the idea by Ito to get, from a mathematical point of view, a better stochastic integral than Ito. But from a practical point of view, we will see that Ito is far better, and therefore, in all applications, in physics, biology, economics, and finance, today we use the Ito integral and not the Stratonovich integral, which is, from a mathematical point of view, the better. But from a practical point of view, Ito is better. Okay, so that gives you a brief history of stochastic calculus, how it developed over time. And now we start basically with Wiener. So we define what is a stochastic process. And then we continue to how to do integration and differentiation. So that is the program for the next hours.